this thing is now belonging. So this thing is belonging to this.
Oh, I see.
So there are coarse grain used to be 20
I see.
Several former universities are now bigger.
I see.
And eventually, I don't know whether the coarse graining is going to.
Okay, more people coming. I would say let's start. So, welcome to the second talk of this morning. Chaos and spatial thermalization and driven-dissipative bosonic tubes.
Thank you very much. I would really like to thank the organizer for this very wonderful week that we had all together. So, thank you, Luca, and thank you for the other organizers. All right, so I'm going to talk to you about chaos in large-scale quantum devices, with a sub-question on how can we think about quantum chaos when the system is open to an environment and driven out of equilibrium by external drives. All right, so this is work in collaboration with those young fellows. So Filippo Ferrari is a PhD student at EPFL, and Fabrizio Minganti is now a scientist in some Alice and Bob quantum computing startup, right? Chief scientist or something. All right. Let me briefly walk you through my language. So, classically, you know that chaos is defined as like exponential sensitivity to initial conditions. So if you start with a bundle of initial conditions somewhere for your system and you time evolve them, and you measure the typical distance, if the system is chaotic, then you will see some typical exponential distance between those two, those trajectories. That's measured in terms of the Lyapunov rate or Lyapunov exponent. Right? And this is if the system is chaotic, but if the system is regular, then you will not see such an exponential growth. Right? So this distinguishes dynamically chaos from regular dynamics. Right? And quickly, people have tried to understand how we should think about chaos in quantum setups. And people have argued that actually one way to go, because quantum mechanically you're losing the notion of phase-space trajectory. One way to go to understand what to do is to make a simplicity stop. Simplicity, I mean that you now convert this classical approach by replacing the Poisson bracket to commutators, quantum commutators, and then you realize that this quantization of this object here is now a square commutator between x and y. And on the right hand side you have this Lyapunov, which is this classical object. Right? And this is to motivate the use for so-called photons, which are typically framed in terms also of square commutators, okay? And presumably are going to tell us something about chaos, dynamical chaos in quantum mechanical systems. All right, so this is kind of a generalization of this piece here. Now for finding HBAR on different operators. Right? It's called low-talk because you go forward and backward in time during your unitary evolution. Right? So it's something that people can compute, but it's something that people cannot measure. Right? It's computable, but not observable. And what do we typically expect of this low-talk? So for those systems that we know are thermalizing, we expect a rapid growth, maybe exponential, maybe bar low, a scrambling time at which then the low-talk reaches some saturation, which is controlled by the quantum fluctuations. When do we know that this growth is going to be exponential? When we know it's going to be exponential for those systems that have first a well-defined semi-classical limit, large N systems, large P systems. Okay, so that was for the time discussion, and now we can also, of course, add space to the picture and people have, experts in the room, people have discussed how operators also are growing in space more than in time. I just wanted to highlight that, okay, so operators are growing, and OTOC now can be defined as position of in time and also in space. So you can really measure the growth of operators with those OTOCs. And everything is protected by this Lieb-Robinson theorem that tells you that, at least for those systems that are locally interacting, so the typical locally interacting systems, nothing can travel faster than ballistic. That's a bound. So there is no supraluminal propagation of anything.
Quick question.
Yes.
So on the previous slide, you said the OTOC is saturating. But then there was a talk earlier this week that says OTOCs should decay as like 1 over T to power D over 2 or something. Like,
Yeah, correct. So yeah, very good point. So my OTOC is the square. Yeah, so generic OTOC, okay. Because I'm talking here of square commutator type of OTOC that are directly the analog of this. In that talk also you didn't see any Lyapunov, or I think you're referring to talk of Ristano. It was not first. This is the first exponentially growing and then saturation. So you have to do some combination. This is hiding the combination of OTOC that is precisely extracting this information about.
So also here there's no space, right? So your saturation is probably 1 over system size or something in a spatial system. So it's 0.
Yeah, so I was maybe too generic. Not all OTOC will. Okay, so this OTOC they will so this OTOC has been computed throughout theoretical physics. So classical nonlinear maps, stat-phys problems, on-math problems, high-energy problems. Okay, and the picture is always the following. So you have a ballistic spreading, a causal light cone, a ballistic spreading with a butterfly velocity that tells you how information spreads in space. And depending whether your system is chaotic or not, then you also have Lyapunov exponent. So these two quantities arguably are fundamental measure of how information spreads in space and in time in your system. And people have computed them in many different setups. I want to highlight not really 3 examples, but 3 ways of trying to understand these laws of OTOCs. 3 typical sets. So I would characterize first the random circuits. And the idea here is that you work with simplified models where you only keep unitary evolution locality. You strip out most of everything else in the physics. Okay? And there you're able to make analytical progress exact. And there you can derive effective field theories for OTOC. And so it really is a nice tool to have theory for OTOC. And in particular, so here I'm taking this example of Adam Naum and collaborators where they computed the growth of OTOC in that particular random circuit. So these are hard measure unitaries, random. You can do it in 1 + 1 or in 2 + 1. Here it's a visualization of the OTOC in 2 dimensions of space, 1 dimension of time. So this OTOC has grown, has saturated, and is now expanding in time at a butterfly velocity that can be computed as a function of the Hilbert space dimension. We can discuss the spread here of the front, etc., etc. That's one way to get analytical handle on this problem. Another way to get good results is ED, so computer simulations, exact diagonalization. This is one particular example, but not that. One particular example of a Heisenberg spin chain non-integrable, so with some local dissolver that is rather weak, much before the NBL phase transition. And people can try to see, so this is again a space-time diagram. This is supposed to represent the OTOC, and we're trying to understand what are the light cones, whether they are ballistic, parallel, etc. It's hard. This is 31 spins. The Hilbert space is in the billions. It's very hard to actually get some large-scale data to have a good feel of what's going on. And there is another approach, which is the effective field theory approach. And this resonates with the talk of Rushira this Wednesday, I think, where here you try to understand how to come up, by symmetry principle, how to come up with an effective field theory for how these things are growing in space and time, right? It was first proposed, I mean, there were some propositions some time ago. So the idea is that, you know, information is not like a conserved quantity, so it spreads in time, so it's more like a fire that propagates, no? It's, so, and actually, very early on, people proposed a combustion equation to try to understand how OTOC evolved in space. So I'm citing here different papers, different people. I'm probably missing some. But okay, so there's one point I want to make is that so when we try to do an effective field theory for OTOC, it's not the same as doing the OTOC of the effective field theory. So starting from hydrodynamics and then computing the OTOC out of it, we'll have a limited limited domain of validity, which is the one of hydrodynamics. In principle, you could also try to start from microscopics, try to get the effective field theory. Start from microscopic, express the OTOC, and then do the coarse graining, then do the hydrodynamics approximation later on. So in that regard, I wanted to make a one-slide detour to report this work that we have done with the Aditi, in collaboration with Aditi, who is here, and Eric Brunet at École Normale, where we precisely do this game. So we start from a microscopic model, okay, and we apply layers of approximations one by one. This is coming from condensed matter, and we get an effective field theory, or at least a kinetic equation for our OTOC in space. Okay, so the particular model that we were interested in, but again, it is more like a toy example, but it was a realistic metal. So we were already introduced yesterday to the behavior of electrons in the metal by in the talk of Kerr. So electrons are interacting from time to time with each other through some inelastic scattering, every 1 million atom. But most of the time they're actually bumping on the defects of the lattice. This is where they spend most of their time, is bumping on defects, which basically introduces some relaxation of momentum. Because they know these defects are random, so you don't have conservation of momentum, so you relax. That's typically the picture for a metal, disordered metal, weakly interacting disordered metal that we typically have in. So this is one possible expression for such a metal. So you have electrons, say, a dispersion relation. You put some local disorder, maybe distributed randomly. That will, once average, will introduce this momentum relaxation. And then you have some interaction between electrons. So you see it's a four Fermi interaction. Here we decided to work in the Cooper channel. But you could probably also work with different electron-electron interaction. Right? So that's the microscopic starting point. But then so you want OTOC. And we start. So it's quantum starting point. So we need to work in the Kellish formalism to express those OTOCs. This fourfold contour that you introduced a bit before. And we work our way through. The idea is to apply the same approximations that one. The idea is first to remap this problem of an OTOC in the Kellish formalism to a kinetic equation. So the same way that a distribution function obeys quantum Boltzmann equation, it was shown by these guys, Leiner, Faurot, and Joffé, that you can rewrite the OTOC problem in terms of a modified quantum Boltzmann equation. Quantum Boltzmann equation tells you that the collision integral will be 0 if you're at thermal equilibrium. So that's the steady state. And the H theorem tells you that this steady state is stable. If you try to perturb your equilibrium, it will relax back to equilibrium, typically. Right? That's the general understanding of the kinetic equation as quantum Boltzmann equation. For that particular problem of OTOC, the quantum Boltzmann equation has also a collision integral, but now this collision integral has two zeros, so it vanishes at 2 points. One is going to be stable, the other one is going to be unstable. So the situation is a little bit different than for the usual Boltzmann equation with relaxation of the probability distribution function to see either Bose or Fermi-Dirac distribution function. Because now the situation is that you start from an unstable fixed point, and you have a flow away from this unstable fixed point to the stable fixed point. And this flow from unstable to stable is the growth of Autok in that language. Right. If I'm not clear,
Sorry, what is phi there?
Okay. So this flow from unstable to is the phi is precisely this. Phi is a measure of this Autok. It's a scalar measure. That measure is basically going to tell you how the Autok is a function of space and time. Phi is a little bit the D that I introduced before.
Does it have a definition in terms of some Green's function, or like?
Yeah. So yes, it has. I can show you definitions. If you want definitions.
Nice place.
Yeah.
Where is it?
Where is the definition?
Sometimes the picture speaks 1,000 words.
Let me change it. Yeah. Okay. So, okay, I need to trace back actually, but okay, I mean I have to do it very quickly, but so this is the quantum Boltzmann equation modified. They modify the. I mean, it's not modified by hand. This is what comes out of the.
So there's a notion of distribution function.
There's a notion of distribution function for Autoks, and this distribution function is a function of x and t, omega and k. So it's a large object. But because we are going to work in the condensed matter setup close to, so at 0 temperature, quasi-particles are going to be well defined. So omega and k, you can lock them together with a quasi-particle approximation. You're close to the Fermi surface, so k is locked to the Fermi momentum. So actually you can reduce this beast. And what I want to argue is that one should probably reduce it in, so you can take moments of this beast, in k space, and you have a scalar moment and a vector moment. A little bit the same way that you would do for the usual hydrodynamics. Now you would look at density and velocity. So of course, then you have higher order objects, tensors, and stuff. This way you can truncate. And the thing is that this kinetic theory that I discussed before is basically giving you PDEs that relate how this guy grows and is coupled to this. So this vector field and this scalar field are coupled in this nonlinear PD way, which we wrote down the equations. And then and Eric Brunet, he's a PD enthusiast, and he was able to solve this set of PDEs everywhere, basically, in all the physical corners. And what I want to advocate is that they look complex, but one thing is first a bit related to Pavel's talk. They satisfy causality. That can be shown mathematically, actually. And then they support different physics. So I will try to. Okay, I was not expecting to spend that much time on this detour, but. So now that I have a bit better defined this, okay, we could call it scrambled, I mean this Autok field basically. We can show that the equation that it obeys is a nonlinear PDE. The left-hand side is reminiscent of the telegraphic equation, where you have wave, kernel, and also diffusive terms. And depending on the relationship between disorder, so elastic scattering and interaction in elastic scattering, which is in this kappa. So kappa measures the disorder in your piece of metal, right? Depending whether this exceeds or not some critical disorder, the term that controls this diffusivity here or this damping may be positive or negative. And my point is that this will drive a dynamical phase transition in the way that OTOC propagates. So it's not totally clear how to see it, but my claim is that if you are, say, in a clean system where the disorder is, say, 0, this is acting like a force that drives the system even more. Okay? And the two terms that are going to be relevant are the wave terms. Okay? In that regime, where the wave equation is dominating, one has to take care of the non-linearities, which I was hiding here. Okay? And the non-linearities are going to become relevant. Okay? And what we're going to get for the propagation of our OTOC field is the development of a shock wave. Okay? So now things are causal, traveling ballistically at the Lieb-Robinson bound. So for us, it's the Fermi velocity. And a shock develops at the boundary of the light cone. But then when you increase this order, this dissipative term now becomes dissipation and now becomes relevant, so you can forget about the wave. I mean, you have to trust me, but you can forget about the wave term. The non-linearities are becoming irrelevant, mostly. And you're back with some kind of a diffusive kernel. Right? And in that case, I'm claiming that the solution of this SPD belongs to the Fisher KPP class. Fisher KPP class tells you that you have a propagating traveling wave that is smooth with some exponential Taylor head. So there is, to summarize, now we are in the presence of strong disorder, strong compared to the inelastic scattering. You have two fronts that are encoded in that equation. One front is the Lieb-Robinson front that ensures exact causality outside of the light cone. And then a second front at a parametrically reduced velocity, a much smaller velocity, which is the actual butterfly velocity, where the information is being scrambled. And this one is described by FKPP physics, so Fisher KPP physics. And the solutions of this equation give you the Lyapunov, and you can compute butterfly velocity, etc., etc. And in particular, you can show that this very nice relation that was introduced by Lamson some time ago, where these chaotic quantities, which are butterfly velocity and Lyapunov, they are related in some way to transport coefficients. So the D here is a transport coefficient associated to inelastic scattering.
I think you mean Mike Blake, maybe? Mike Blake?
I think Damson also had some, no? This
Not
is
that I know, but yeah.
Okay.
Maybe.
How universal are you saying that relation is? I mean, is this a statement that's specific to these dirty metals, or?
yeah, so
I thought that Mike Blake stuff had to do with holographic theories.
yeah, no, I'm not saying that this is the same derivation. I'm saying that. So I think our setup is well, it's a condensed matter setup. So I don't think the precise, the precise dispersion relation, the precise way that you inject disorder, the precise way how you put interaction will matter to that eventually. In the case where disorder is actually overpowering the disorder is really what the first time scale.
Maybe even in the holographic context, it's not generic. Yeah, but in some limits, it applies. Large N.
At least it gives one relationship that that puts on one side scrambling and chaos, and on the other side transport.
Dimensionally correct.
But maybe one complaint about this formula is that these things exist. So the Lyapunov exponent you could only define in a semi-classical system. Whereas butterfly might be more general. Diffusion is much more general.
Sure. So
Yeah.
the short answer, of course, was this is not the theorem or anything, but But I think when you have say you want transport, maybe that that could be a guide. I'm not saying.
Well, you need large N for lambda to exist.
Sure. Large N you can always lambda. I think if you coarse grain, if you don't have
you really need a large number of local. You need semi-classics to define a Lyapunov exponent.
you can always coarse grain space to get your.
No. Spin chains don't have Lyapunov exponents.
You need large local Hilbert space.
Large local.
Like
Yeah. So it is, very special.
Sorry, can we just, in that equation, the boxed equation, D enters in kappa, is it? Effectively?
Very good. So these coefficients, they have. So these coefficients is a bit like related to Kurtz-Stochastic. These coefficients, they are effective coefficients. The way that they depend on temperature, they depend on everything. They even depend on each other. So, for instance, the more disorder you have, the more interaction you will have because of the phase space constraints you relax. So it actually disorder enhances the impurity scattering, the elastic scattering. So they depend on a zoo of stuff. I'm taking them as phenomenological parameters, but people have written books on how they depend on everything, temperature, dimensionality, and.
No, so my question is this non-linear term in this equation, phi cube, that's not really needed, right, for getting.
So this phi cube is phi cube is needed for the saturation. So this is what tells you that there will be eventually some saturation of the OTOC. But this is what I learned from Eric from the FKPP. FKPP is a nonlinear PDE, typically you can put. But actually, when you care about just the traveling wave and the geometrics of the traveling wave, the kinematics of the traveling wave, everything is already encoded at the linear level. So this is why I said that it was irrelevant in some sense, that irrelevant in the sense that this information of butterfly velocity, Lyapunov, they're already encoded in the linear part. The nonlinear part that is coming from the electronic interaction, we need it, of course. Yeah. But eventually, a posteriori, I can say that this kind of irrelevant information.
So it has no effect on the slope?
No effect on slope.
So you're saying that VB doesn't depend on U?
VB does not
Doesn't depend on the strength of the interaction? Or?
VB, well, okay, so VB will depend.
No, I think it does.
It does. No, VB depends on the disorder. Actually, it's reduced by disorder. So, and disorder, again, disorder depends on everything. So everything depends on everything. Because it's really phenomenal. So now I'm back. Okay, sorry, long detour. I'm back to chaos in bosonic systems this time, and I want to argue that as people are trying to build for the quantum computer, they go to larger and larger system sizes experimentally, and the more particles or the more degrees of freedom you put in a system, the closer you're going to get to chaos. No, this is because the more particles, the more chaotic. And equal to 3 particles, we cannot solve. So more particles. So there's one thing, and all these quantum computing propositions, they are usually built also on some strong or some pretendedly strong light matter interaction. So you need nonlinearity to be strong, which is also bringing you closer to chaos, because nonlinearity is bringing integrability, is going to bring you some chaotic dynamics. And second, you are putting more and more degrees of freedom, so you're going to be more chaotic. So people are now realizing that chaos is really looming on the quantum computer, and they need to find proper mitigation protocols for mitigating chaos. So this is one of these paper where they actually study the different quantum computers that are available, IBM, Google, and stuff like this, and discuss chaoticity in that in this context. And what I'm interested in particular are light matter interaction systems. So this is a CQED platform, circuit QED platform, where you have basically a bunch of optical resonators, photons living there, that are non-linearly interacting with transmon qubit, right? So this is a sequence of 72 non-linear quantum oscillators. Okay, and because this is live, these systems are always coupled to some environment, even just to operate them. So they are lossy systems. So you always need to inject new photons in the system, so they are driven out of vacuum. So it always come together. No? So they are lossy, non-equilibrium driven-dissipative systems that are in principle inherently out of equilibrium. All right, so this is in the group of Andrew Hauck at Princeton University, but there are many other examples in around the globe with different platforms also, etc. What they show is that these photonic resonators with nonlinear coupling, you can basically see them as a Bose-Hubbard chain. Okay? This is in 1D. A Bose-Hubbard chain where you have your harmonic oscillator, your Kerr nonlinearity here, and the hopping from one resonator to another. Okay? And because you always need to inject photons somewhere, so this is at the first site, you would drive it with some photonic drive. That was actually the Hamiltonian I wanted to show. In principle, you have this is the frequency of your pair oscillator, and this is how you time dependently drive with a continuous wave your electric field at the first site. So then you can go to some so-called rotating frame and basically get rid of this time-dependent Hamiltonian by working with the rotating frame. Now the frequency of the oscillator is going to be shifted from the bare frequency to the frequency in the rotating frame, which you have to subtract the drive frequency. So what matters is actually this delta here that can be positive, negative, etc. These things are operated in the gigahertz. I mean, this typically this gigahertz. The nonlinearities don't manage to do very good, so it's typically a weak nonlinearity. All right, and they have because it's coupled to some environment. They also have dissipation typically at the boundaries. So here and here, you will have some decay, okay, that you can introduce with some Lindblad master equation. So you have the Hamiltonian evolution plus the decay at first and last site. Okay, with some gamma, which is telling you the rate at which you dissipate your photons. Right? Again, these are operated at very low temperatures. The Hubbard U is kind of small compared to all the other scales. Okay, so this is a Bose-Hubbard chain out of equilibrium and coupled to some environment. And okay, so it's an interacting problem. It's not integrable, so in principle we would expect it to be a chaotic system, but I want to ask, how do we actually probe for chaos in those systems? And if we show that this system has some sense of chaos, then does it thermalize? So now my theoretical system is going to be this one. So you drive on one end, you dissipate on the other. Actually, you dissipate on both ends. Okay. But in between, you have a perfectly fine U1 preserving bulk. Okay, so you have charge conservation here. Actually, you have also momentum conservation, energy conservation. So everything is conserved in the bulk. But things are being broken by the boundary here. This is breaking the U1, and the dissipations are weak breaking the U1 symmetry.
What do you mean by momentum conservation? You're not conserving momentum here, right?
No, I'm saying this is translation invariant. So then, if you send some wave packet, it will momentum will be conserved. So the setup is good. And this setup has been actually very recently studied by two groups in the classical regime. In the classical regime, where you take the quantum fluctuations to 0. So there's the first group by Shivashi Sondi and a second group by Abhishek and collaborators. And the classical version of what I presented to you is just the Klein-Gordon chain. Okay, nonlinear oscillators that you drive on one end and also can dissipate on both ends. This has been studied by these two groups. This is the slight difference with the model I presented before. Is here, in that particular setup, there's no U1, there's no conservation of charge. There's no U1 symmetry for those oscillators. Okay, so it's slightly different, but still, they looked at how this thing was behaving as a function of the driving strength, right? And they found amazingly rich phenomenology, right? So they found at very weak driving, some quasi, I will go into enter some more details, but some quasi-linear regime, okay, where basically the Hubbard U doesn't play any specific role because it's not activated. Then some nonlinear hydrodynamics, where here you have some kind of local thermalization.
Sorry, what is F again?
F is the driving strength, yeah. F is
Ah, yeah.
it's here.
FD, so.
And then an abrupt transition to some nonlinear resonant wave regime, where you break spatial symmetry and have a modulated phase and ballistic transport.
For nonlinear dynamics, you mean KPZ?
Oh no, I meant no. Okay, so the termination is not well. No, I don't mean KPZ. I just mean hydrodynamics in the presence of nonlinear terms. Okay, my terminology may not be the
For zero driving, you would see like KPZ physics, right? You would see.
For zero driving, photons are leaking out. You have nothing in your chain, so you are basically vacuum. So if you want photons, you need to.
Finite temperature, you would see KPZ.
Yeah. So actually, Abhishek. So this Abhishek group. I mean, maybe Abhishek can tell more, but they tested both scenarios at zero temperature, coupled to some dissipative bath, and with temperature, and looked at the stability of this regime as a function of thermal fluctuations.
Diffusive, so there's no KPC.
Sorry?
It's just diffusive because there's on-site. I mean, there's no momentum conservation. So it's just diffusive.
Because the Ford potential is on site.
So is this operated now in the basically analog of high temperature, so no condensation, no basically.
Yeah, you're in normal phase. Normal phase. Yeah. Yes. So we went. So of course, I mean 72 oscillators. You can do it classically, but quantum mechanically, you need some strategy because this is not going to work. So the strategy is to actually use the fact that the nonlinearity is weak. We're going to inject, because the nonlinearity is weak, when we drive the system out of equilibrium, it's going to actually get a lot of photons, and the density of photons we're going to see is kind of high. So we want to work in this semi-classical regime. Okay, these are actually operated in some semi-classical regime. So we're going to use a formalism that allows us to work in this semi-classical regime, and for that, this is a technical slide, but just to tell you that we have to map our Lindblad problem, Hamiltonian plus dissipation, to some kind of stochastic classical equation, and the vessel here is the so-called Wigner representation. The Wigner representation is just basically a Fourier transform in the basis of Fock space of your density matrix and actually of any operator in your quantum world into Bayes symbols. And the way that you consistently expand in powers of h bar is by expanding this Boyle product here. I'm not entering too much details, but then you have a consistent way of tracking the h bar and then stopping at the order that you want. So if you do this Wigner representation of this Lindblad master equation that I showed you before, you have now a beast, but it's a differential equation for this Wigner representation of your full density matrix of the full system. Okay, you can write it down, and so you can recover the different terms. This is the hopping, this is the drive, this is the nonlinearity, and this is the coupling to the band. Okay, and the truncated Wigner approximation, which is to stop at first non-trivial order in h bar, is basically to kill all the derivatives that are third order and higher. Okay, the so-called truncated Wigner approximation. And then, if you really carefully look at this leftover, you'll see that you see a Fokker-Planck equation. Okay, so now this Wigner function becomes a well-defined positive probability distribution function for finding the state of your system in some given coherence. Right? So now we have a notion of a Fokker-Planck equation. And Fokker-Planck equation, you can map it to a Langevin equation. And what you get is basically a set of stochastic equation for your local degrees of freedom, which are this alpha and alpha star. Okay, which are the photonic degrees of freedom in each case. Is it clear? So we went from Lindblad to a stochastic set of classical equation, a set of classical stochastic equation, But now the beauty is that this you can put in a computer because this is a linear set of equations, and this you can solve to hundreds of sites. Okay. But it still retains a little bit of quantum mechanics. Quantum mechanics is first is in the noise here, and quantum mechanics is also in the initial condition. I didn't tell you, but you have to prepare your system with some random initial condition, and quantum mechanics is also here in the initial condition. And then you can solve this set of stochastic equations on your computer, and this is a typical trajectory, quote unquote, that you see, so it's very random. And the idea for us is to go to the non-equilibrium steady state. So you have drive, you have dissipation, eventually things will balance out, all right, and you expect some non-equilibrium steady state. So you wait long enough to be in the non-equilibrium steady state, and then you start doing statistics of these trajectories, okay? And the statistics, as I said before, they're going to give you these Wigner probabilities, Wigner functions, okay? This is Wigner function in the complex plane that tell you what is the probability for your field, your photonic field here, to be in that particular state, okay? Okay, so now let me try to tell you, and from that statistic, then you can compute all the observables that you like, photon number, current, you know, stuff like this, entropy, stuff. So now that's the picture. So now again, so I'm increasing the drive F, okay, from 0 to some large value. So at 0 again, no photons no photons anywhere because they're leaking out. And you start driving. You have a dilute gas of both particles that are barely interacting with each other. Okay, so it's mostly a non-interacting gas. And so the system is dilute and the Hubbard U is not really activated. Okay. Then you have this nonlinear regime where Hubbard U is activated, and then I will argue that this is a hydrodynamic regime. And then again, we see some nonlinear resonance wave regime, similar to what had been shown in the classical case. I will mostly work in that. I will mostly report results on that particular hydrodynamic regime for the purpose of this workshop. Okay, so let me come back now to quantum chaos and OTOCs. So how to probe for chaoticity in that particular system. So one way to do is to look at, so now basically now we have trajectories. So we have the notion of trajectory, so we can apply the notion of OTOC that I gave you in the very beginning, the semi-classical version of OTOC, where you can look at trajectories and how they diverge exponentially or not as a function of time. And one way to do, for instance, is to look at how, so by jiggling the phase here in the first oscillator, how two same system but with slightly different phase initial condition here will give you a will give you a phase difference here at the last side. Okay, so you measure now the exponential divergence of trajectories from that side to that side. And that experimentalists, in principle, they can look at the phase in the first side, and they can look at the phase in the last side. Okay, that's in principle something that one can do. Okay, because phase is not really a proper quantum mechanical operator, we're actually working with exponential of the phase. But at the end of the day, what it really means is that we're going to look at two copies of the system. We're looking at the phase. So you two copies of the system. You do a little change of phase here at time t. Okay, the first side, and then you look at the difference of the phases at time t plus tau. Okay, and then you take t to infinity because you want to work directly in the steady state. And this distance is actually encoded in the cosine and this concept of the math. And so this function is really a OTOC, okay, directly in the non-equilibrium steady state, okay, and we can plot similar phase-time diagrams. So this is supposed to be a cone. I mean, I'm just showing you half of the cone, where you see the ballistic butterfly velocity, and outside of which it's causal, you have nothing, and it's inside of which the OTOC is growing. Okay. And now I have to tell you, depending on which regime I am, what is the OTOC doing? So I'm claiming that in this quasi-linear regime, where Hubbard U is not activated, and in this extreme regime, basically the growth of OTOC is going to be bar low plus some oscillations. Okay, and it's actually going also to saturate to some lower than ergodic bound. Okay. These are not exponential growth. These are not chaotic growth. Right? But in that nonlinear regime, we have beautiful. This is now in a semi-log plot. Beautiful exponentials. Okay. So now I'm doing different cuts at different times, and you can see them arriving at different times that are related by this butterfly velocity. So you have the traveling wave of exponentials that are coming one after the other. Okay. And from that you can extract the Lyapunov, the butterfly velocity, etc., etc.
Could you comment on how these plots are obtained, like in practice, like what is being solved here?
Yeah. So. Okay, so I cannot come back. So you remember the stochastic equations? So you wait long enough that you are in some steady state. This is stochastic. And then you take you stop at some time in 500, let's say. You copy this into another solution, and this solution you slightly perturb the phase at first sight. And then you run, these two copies, you run them again with the same noise history. Okay? And then, after some time tau, you look at how the phase in the left side, how the two phases of your two systems, two copies, they are now far from each other.
Where is the phase in the stochastic equations?
So the stochastic equation was, okay, it was not very good. The stochastic equation was on this complex field alpha. And this I'm writing as r exponential I phi. So this was the phase.
Oh, it's that phase that is being. Oh, okay.
That people can measure the phase with some weak measurement. Yes. 10 minutes. Okay. Is it clear? Or? Okay. So okay. So here is a proof that this regime has chaotic, so it's a non-equilibrium regime, but it has a chaotic character. And now we can ask, well, it's chaotic, so how should we think about, so we're directly in the non-equilibrium steady state, things are being driven by one end, so we're going to set up a, you have some drive F, a system, and then you're coupled to some zero temperature thing back. So maybe we can try to think of how, if this is being driven out of equilibrium here, things is chaotic, maybe things will thermalize, but not in time, but in space. We're directly in the non-equilibrium steady state region. Okay? So the question is, how does this system thermalize, not in time, but in space? Okay. So what happened, so now I need to, so this system had a U1, so the system had a U1 symmetry that was broken by the two ends, okay? And I need to tell you how, and I'm going to argue, the general argument is that because you have this U1 symmetry, amplitude is going to relax on hydrodynamic scale because the system has to find a way to get rid of actual photons, but for that you need to throw your entire system, go to the air, come back, etc. But the phase degree of freedom, so we have phase and amplitude degrees of freedom. The phase degree of freedom is going to relax very quickly. So quickly, so this is the first side. Quickly after the first side, the claim is that the phase degrees of freedom, they quickly thermalize to some disordered state. Okay, and the average phase, which is plotted here in red, quickly goes to 0. Okay. But for the other degree of freedom, which is amplitude or photon number, this has actually a very long plateau until finally it can find a way out of the system. So there is a protracted hydrodynamic regime. Okay. This restoration of the, so quickly what I'm saying is that you quickly restore the U1 symmetry in your system. Okay? And this you can easily see by plotting this Wiener function in a complex plane, and you see that if they are symmetric like this, it means that you have U1 symmetry. Okay? Okay. Okay, we are not, yeah, so if it's, so now we want to understand the hydrodynamic description of this non-equilibrium steady state, and for that we need thermometers. So we are going to basically want to understand, so we have this U1 that is restored, so presumably there is a chemical potential, an effective chemical potential in the system. You have an effective temperature in the system that are being defined locally, and we need some local thermometers. For local thermometers, we do usually, I don't know whether it's usual trick, but you can think of try to think of your system as a product of Gibbs states. All right, Gibbs state with Hamiltonians that are basically the nonlinearity, but then you have to find out what is the temperature of this local thing, and what is the chemical potential of this local thing. So that you can solve. So given the data, given all the numerical data, you can try to see whether this fits, and this fits perfectly. Well, this doesn't fit perfectly close to the drive because this is not the U1 restored phase yet, so this will not be the correct Gibbs state, and this is so presumably not a thermal state very close to it. But as soon as you have U1 restoration of your that U1 is restored, you have a local description that you can do in terms of Gibbs states. Okay, don't want to spend that much moment, but you can also have different thermometers. So we also look at different versions of thermometers that are impurity models, so driven-dissipative impurity models that will give exactly the same results. So now you can extract the chemical potential, the effective chemical potential as a function of the position of the chain. So this is first side, last side. You see that you have an effective chemical potential that is positive. Is really trying to put photons into to populate your resonators, and then it crosses over to 0, and then you have this domain here. Where chemical potential is negative, so basically it wants to deplete the photons out of your chain. What was a bit more complex to make peace with is the temperature dependence. So let me try to, so how should we think about temperature in that system? So we're connected to a 0 temperature bath here. So definitely temperature, I would expect it to decay to maybe 0, or at least to decay the closer you get to the 0 temperature bath. We're also connected to a 0 temperature bath here. Here you have some injection of energy, which is a coherent injection of energy, so it has not yet had the time or the space to transform into heat. So here I would also expect temperature to grow because you are close to a 0 temperature bath. Energy is not yet in the form of heat, so temperature is probably on the rise if temperature can be defined in some way. So somewhere in the middle there should be some maximum or something. The fact that this is peaking like this and the location of the peak was puzzling to us for a long time, and I think it's still kind of puzzling. But basically it says that there are 2 domains in that chain. One domain which is kind of trivial domain where temperature goes down, and if you have a flux of energy, this gradient of temperature is going to try to push heat outside of the system. But this growth here means that if we believe in, you say, Fick's law or anything that the thermal gradient like this tells you that you should have some heat flow, at least one component of the heat flow from that is in the wrong direction. Okay, so there are 2 contributions of the heat flow. There's going to contribution from the drive that is on one end on the system, and this heat flow that is coming from this gradient of temperature, and the 2 somehow assembled together. Why is the system shooting up a temperature like this? It's probably because it cannot increase the number of photons. So number of photons, as we said, is number of photons is saturated. It's saturated because of the nonlinearity, so it's hard to put more photons in the system. The nonlinearity is actually n squared, so the potential energy is also saturated. So the only possibility for the system to put more energy is actually to grow the entropy. So the entropy will grow, so we didn't show, but there is also plot of entropy. The entropy grows, the temperature grows, and this is how the system finds its way to make up for this energy input. Okay, so I'm plotting exactly the same thing here, but now in terms of this high-dimensional quantity, which is 1 over temperature times chemical potential, so it's simpler to discuss. This is, and I'm saying that whenever the chemical potential crosses 0, this is a regular thermal phase. But before something strange is happening with this gradient of temperature, it's still a locally thermal phase, but the way that it evolves as a function of space is not totally trivial. And so we call it pre-thermal. And you can measure the size of this phase as you increase the system size. So now you define this length here as the length of the pre-thermal phase. and you repeat your experiment for different system sizes, and you see that this pre-thermal phase grows linearly, so it's really a thermodynamic phase. It's a non-equivalent thermodynamic phase, if you will. Alright, so this finishes my talk. Okay, I wanted to make a simple point that chaos is in principle looming over the large-scale quantum devices. So we need to find mitigations for chaos. Then I try to advocate the fact that you can define chaos semi-classically for non-equilibrium steady state. So that gives you a handle on chaos for systems that are quantum, out of equilibrium, and connected to some environment. And in that particular setup, we have discussed a two-stage thermalization space. So first, quick relaxation of U1, effective chemical potential, much longer protracted relaxation for the amplitude degrees of freedom, and in between this pre-thermal phase with a temperature that shoots up, and where if we want to continue, we should probably look at transport and understand why the transport is super diffusive, etc. Thank you.
Questions?
Maybe about this second point here. I mean, can you maybe see some structural differences in the chaos that you have in these systems where you don't only have a Hamiltonian generator of dynamics, or maybe not yet, or is that?
That's a very good, interesting. So we have not. So the old talk. So I showed you quickly some. We have not done the precise analysis of what's going on, but that would be a good thing to do indeed. Yeah, to see whether the Limblad terms are playing any role. That's a fair question that in principle can be asked even simpler. Yeah, question.
So, so one notion of quantum chaos that's used a lot is RMT, either statistics of the spectrum and so on. And so there, I think there have been generalizations to Limblad systems.
Yes.
I guess
So
you're not happy with these.
No, so the Limblad. So the Limblad is the generator of time translation, the same way that Hamiltonian is generator of time translation for Hamiltonian. So you can, in principle, look at RMT statistics of your Limblad. So these are now non-Hermitian matrices, and so. But the connection between RMT statistics and Lyapunov is already not,
Right. Yeah. But something appealing about RMT is that you can apply it to any quantum system that may or may not have Lyapunov beyond semi-classical systems.
I have two before. Okay. What are the difference?
I don't know if you say.
What are the difference between the quantum setting and the classical setting? I mean,
So
that's done by the.
Yeah, so the difference. So first is I think there is the U1. So we have a U1 conserving model. That may not be such a big deal at the end of the day. Second, we have the quantum fluctuations. So quantum fluctuations, they are appearing in the noise of my stochastic equation. Okay, and in the initial condition of the stochastic equation, which is quite important. You need some initial condition that has a.
Okay, it's methodology, but result-wise.
Result-wise. Result, yes. That's a fair question. Result-wise. Most of the quantum features are going to be,
In the strong over the dry?
yeah, this is in that phase that I didn't discuss that much. This is where the quantum mechanical effects are going to become important. So, the question is, are quantum fluctuations, is it stable to quantum fluctuations or not? And this periodicity and the thing that I discussed, how is it affected by quantum mechanics, by H bar? This will be, so I didn't report, but so basically the most prominent quantum effects will be in that regime. In the hydrodynamic regime, I think one could make a case that it's
in the hydride regime,
that is sorry.
So in the high drive regime, doesn't it become even more classical? I mean, you have a lot of bosons and...
No, absolutely, yeah. But that's why we do semi-classical analysis. And the result...
Even in the high drive, if you go further, will it not become more and more classical, or...?
This is not what we see. So then the effects of quantum mechanics is, yeah.
So how do you characterize the effects of quantum mechanics?
Well, for us, for instance, would be so we have knobs, no? We have and practically we have these knobs of stochastic noise that you can turn on, turn off, and so this is the RH bar, and you can follow. But yeah, no, I'd say that it's a fair point that at the end of the day, what we find here, phenomenologically at least, is precisely the thing that I think those groups have found also classically. But I think this is hydrodynamics. Okay, you have to check, but in that case it was hydrodynamics, and then it's classical.
But the classical model for this would be exactly that one?
Not exactly. The one thing is there's a different symmetry group, but
okay, but in principle can be done. And it would be nice to see if there is anything quite.
But I think this is a fair generic question. Like, what is quantum in hydrodynamics? No,
I agree. But even in the evolution of the Lyapunov, right?
Still a generic question that is interesting.
So this position of the peak in the temperature, what does it depend on? Maybe you mentioned it.
So it depends on system size mostly. And so as you increase system size, this peak will shift. So it's the distance to Earth.
I see. But does it depend on some hopping parameters within the Hamiltonian and so on?
Oh, yeah, no, sure. That we didn't study, but sure, it depends. I mean, temperature in the system is a balance between drive, dissipation, the heat. So it depends. So it's a balance between basically all the processes that are here. So it depends on everything, I would say.
But you don't know how. No, as a function of system size is fine. But for a given system size, does the peak move linearly with coupling or with drive?
With that you can probably make some heuristic argument, like if you increase I don't know, if you increase the nonlinearity, probably you have more heat. I don't know. We can probably think of how it should grow. But yeah.
Okay. Questions? Then say we thank the speaker again.